properties, such as it is a superconductor, but the TC is relatively low. And its gap is reported to be nodal from the heat transport and the RPS measurement. But whether it's a D wave or S wave with accidental nodes is still under debate. And in this system, the electron correlation is strong. Gamma, the small field value, gamma is about 100, and it has orbital selective mode transition. And also in this system, the spin fluctuation is different from the parent compound. It's deviated from pi 0. And it has been reported by an NMR study that it has a possible new nematic state. Now this page shows the previous STM and RPS study. Compared with the heavily, the optimal doped iron-based superconductor or parent compounds, the study in this kind is 1-2 whole doped system is, I think, is still limited. So the previous STM is only focused on the potassium 1-2, and they observed such a density of state peaks around the Fermi level and a small superconducting gap. And the RPS study shows that there's three hole-like electron hole-like pocket at the center of the Brownian zone. And there's one RPS study on the rubidium 1-2 system. And but compared with the potassium one, the data is not as clear as the potassium one. They only observe a single hole pocket at the gamma point, and they claim it is more consistent with the single iron Brownian zone, the unfolded Brownian zone, because the interlayer spacing is larger for in this system. Maybe its folding is weak. So our study is performed in this dilution STM. It has a base temperature of 20 millikelvin. So in this study, our energy resolution is about, or the effective temperature is about 300 millikelvin. It's calibrated on the aluminum film, but so now the resolution is improved to like 160 millikelvin. So we can correctly resolve the U-shaped superconducting gap of the aluminum film. Now here shows the topography of the cleaved rubidium 1-2. So here I show two types of surface A and surface B. Actually, surface A is the mostly observed, about 90% chance to observe surface A. But actually, these two surfaces, the lattice is the same. The only difference is their symmetry breaking in the density of state or in the DIDV mapping is different. I'll show it later. But in the DIDV spectra, they both show a DOS peak at the Fermi level, which is similar to the potassium 1-2 system. So firstly, we should clarify the surface lattice structure. So here we can resolve the surface lattice. The surface lattice is actually showing here. It is a square lattice. The lattice content is about 5.4 angstroms. And it is actually corresponding to a √2 by √2 reconstruction. It is formed by the surface rubidium atoms. And the surface you can see here is a lot of hollow-like defect. They are actually the rubidium vacancies. The smaller one may be a single vacancy, but the bigger one is it's not a single vacancy, but maybe 2 or 3. And so in the vacancy, we can resolve actually the arsenic lattice beneath the surface rubidium lattice. because its lattice constant is exactly the lattice constant of this material. So then we can say that the surface lattice is indeed root 2 by root 2. The reconstruction, so so it is half coverage. The rubidium is of half coverage, so it is a non-polarized surface. Now here it is important to notice the surface lattice is still C4 symmetric. It doesn't break the C4 symmetry. And these are some details of the lattice. So in this model, if the rubidium has a root 2 by root 2 reconstruction, there are actually two equivalent occupation sites of the rubidium atoms. So the orange one and the dust square, the dust cycle. So there should be two different domains. So we indeed observe this domain. In this image, we can observe the domain walls, and the upper domain and lower domain, they have a half unit cell offset, as shown here. Then we check the superconducting gap, and the gap is uniform and on the surface, and it's V-shaped. On type A and type B surface, they are slightly different. On type B surface, the gap is a little bit smaller. This shows the fitting of this gap. So they are V-shaped, which indicates there are possibly nodes in the gap, or at least the gap should be strongly anisotropic. So we can fit it with the nodal-like gap and get a well fit. If we use the iso wave, the fitting is not as good as the nodal one. And here I also want to say it's V-shaped. That doesn't be due to that our resolution is not high enough. That's because on the aluminum film, the gap is even smaller, but it is is a fully gapped iso wave. We can still resolve it. It's gap bottom here. Right? It's still like U-shaped. So we perform the QPI measurement and do the dy/dv mapping on the surface. Now you can see on the surface A, so the mostly observed surface, it shows a C2 symmetry. That's the symmetry breaking. The FFT pattern of the real space mapping is twofold symmetric. On the surface B, the anisotropy is even stronger. And now you can see the FFT gives two arc-like feature. And if we plot the FFT in the Blazing zone, you see the symmetry breaking is along the pi direction. Yeah, which is different from the previous results on the pyrene compound, which is along the 0 pi direction. It is along the pi direction. So we can also compare with the RPS result. The RPS result observed as a single electron single hole pocket at the gamma. And they appears to be consistent. But here I want to say that this map is FFT, so it is in the Q space. If we assume it's not direct mapping of the Fermi surface, it measures the scattering between the Fermi surface. So usually for a round-shaped Fermi surface, Q equals 2K. So this pocket, if we change into K, it should be only half the size of this pocket. So it appears to be a little bit smaller than the RPS measured Fermi pocket. So actually, we're not sure if the band measured by QPI is the RPS measured one. But band dispersion is clear. It is a hole-like band. And for the type B surface, you can see if you take a line cut along different direction along pi pi or pi minus pi, that the dispersion is very different. So that's the C2 symmetry. And the C2 symmetry is also reflected in the magnetic vertex mapping. On the surface A, we apply the perpendicular field, and we can observe the vertex, and it's elongated along the pi pi direction. And in the vertex core, we can see the vertex state. On surface B, the core, the shape is even more anisotropic. But at the core center, you still see the peak close to the zero bias, right? But now it's not a zero bias peak. It should be, actually there are many peaks. We see an envelope of these peaks. And we can take a line cut along different directions of the vertex. And you see the coherence length can fit from this line cut. And they are different along the two particular directions. So previously, people also use the SCM to measure the nematicity in the iron-based superconducting system. So for example, in the calcium 122, the parent compound, they also see an anisotropic QPI, and in the iron cyanide, they observe such elongated vertex core. These features are all considered to be the evidence of the nematicity, but they all along the pi zero direction. But our observation is that they are along the pi pi direction. So it's like a new kind of nematicity. So next part is we also check the superconducting gap. We want to know, it appears that there are nodes in the gap, but we want to get information from our data to see whether it is the S wave or a D wave. So firstly, we check the impurity effect on the surface rubidium vacancy. So on this single vacancy, you can see right on the vacancy side, the gap is indeed like a suppressed a little bit. Yeah, it's not a strong suppression. You just see the gap bottom is a little bit shallower than the gap measured away from the vacancy. Actually, the conductance at the zero bias is proportional to such suppression. So we can plot the decay of the zero bias conductance from the vacancy center to the outside. The decay length is about 1.4 nanometer. It should be the range of if there's an impurity induced in-gap state. This should be the range of this impurity state, the spatial distribution of this impurity state. And on the type B surface, the result is similar. So another way to get information of the gap structure is to check the response of the gap on the step edges. This is because if there's a gap, if there's a sign change, it's another gap with sign change, such as a D wave. If the step edge is facing to the nodal direction, so the quasi-particle reflection at the edge will have a sign change. So in theory, that will give rise to an Andreev bound state. Actually, a zero bias peak. Now this is indeed observed on the bisco, the cleaved surface on bisco. There are step edges. You can see close to the edge, there's the in-gap state here. And on our rubidium 122 surface, we also observe different oriented step edges, like one edge along the 100 direction or along the 110 direction. So we check the behavior of the gaps along this edge. So we take line cut along this edge, and you see the gap is indeed suppressed right on the gap edge. But we don't see a zero bias peak, just see a small suppression. But if we subtract the spectra, the box spectra, you can see a peak appears. And but what we see is that the behavior are still different for the 100 edge and the 110 edge. And the difference is that the decay, the suppression of the zero bias conductance, the decay of zero bias conductance is different for these two edges. So for the 100 edge, the decay is fast. For the 110 edge, the decay length is much longer. So we think this two different behavior. Maybe from the an indication is that it is the 110 edge faces the nodal direction of this D wave parent symmetry. Because the D wave, the dx square minus square wave, there is a gap change, the sign change along this direction. Right? So along the 110 edge, there should be a Andrew bound state. But on the 100 edge here, there's no sign change during the reflection. So there's no Andrew bound state. The decay of the Andrew bound state should be the coherence length. So it is longer than it should be longer. The decay length is long. It's longer than the 100. But for this such extensive S wave parent, both the 110 and the 100 edge has no sign change. So you only expect the Andrew bound state on these edges. So our results is more consistent with this D wave parent. And we also checked the surface doping effect. So if such the unusual nematicity only happens in the heavily hole doped region. So if we dope the surface away from the whole region, heavily hole doped region, such as we dope with potassium, it gives electrons on the surface. And then we can see what happened. So we do this experiment. Actually, it's on another STM system. We dope with surface with different amount of the potassium atoms. So I can see the topography and a certain coverage, 0.17 monolayer. Here, the 1 monolayer is the iron density of the iron atoms in the iron arsenic layers. So at this coverage, the surface is flat. Actually, it formed ordered structure. And as the doping, as the coverage increase, the potassium coverage increase, you can see the spectra involves. And at this coverage, there's a bigger gap, a larger gap showed up. And this gap has a size of 7.5 millivolts. It's much larger than the gap on the undoped surface, which is 0.5, about 0.5 millivolts. So we think it's due to the electron doping. Actually, at this doping level, it is close to the optimal doping, optimized doping. So we check the QPI before and after potassium doping. So before the doping, we still see this such C2 symmetry breaking, which is also along the pipette direction. So here we can say so we can repeat our results on different samples and a different STM system. But after the potassium doping, you see the C4 symmetry is restored. I show the perfect C4 symmetric, full symmetric QPI patterns. We think it's because the electron doping drives the system out of the whole Doppler region, so the nematicity disappeared. So we can plot this phase diagram. So close this to this 3D 1.5 configuration, which is the potassium 122 system. There's a pi nematicity or fluctuation. So such C2 symmetry breaking is also observed above the TC. So there could be a fluctuation. But at the optimal doping, the nematicity would disappear, and the electronic state recover to the tetragonal. So the possible origin, I think recently there are several theoretical papers suggest there could be different origins. Actually, I don't quite understand. I think, but I think some of the authors are here. We can have a discussion. But I know for the pi zero nematicity, it's closely relevant to the stripe AFM. So they can distort the Fermi surface and give you a unsymmetric QPI pattern. And for the whole DOP system, so in this paper, they predict that the spin fluctuation change from the pi zero to pi. I think it may be an origin of such a pi nematicity. So in summary, we observe a C4 to C2 symmetry breaking. And it's along the pi direction. And we observe the V-shaped nodal gap and the long-range gap suppression along the 110 direction would stress the gap nose is in this direction. It's more consistent with D wave pairing. Okay, here I will just list the recent work on related system. Yeah, thank you.
Okay, yeah. So any questions? I mean, if not, I'll try to ask some questions, yeah. Oh, okay, yeah, Pablo.
Yeah.
The QPI patterns that you presented, were they measured above TC or below TC? And a follow-up question to that is whether you tried to fit, with different gap functions to your QPI patterns, because in principle, QPI contains phase-sensitive information about the gap too.
Right. In this QPI, in this data set is measured below the TC. But we also check the QPI above the TC here. It shows a similar patterns. You are right, the QPI may also give you the information on the gap structure, but we tried that. But the QPI is, be honest, the QPI is not, the pattern is not clear enough to get information, to extract the information, I would say. So far, we cannot get useful information about the gap structure from the QPI.
Finally, is there some critical temperature below which you see the nematicity, or you see it for all the temperatures measured for the rubidium sample?
A critical temperature, but we didn't check the transition temperature. That we need to vary the temperature. But for the STM, it's kind of difficult to vary the temperature. We only check the measurement at the QPI at low temperature, at the base temperature, or at the helium temperature.
Okay. Thank you. Thank you very much.
Yeah, so I have some questions. So I mean,
Actually, can I just ask about this temperature? Just
Okay.
clarification, if you don't mind. So, Tom, is 4.5 Kelvin, is that below TC or above TC?
Above TC, yeah. The
Okay,
TC is about 2.5 Kelvin.
great, thank you.
yeah, okay. So I have several questions. So I mean, it looks like this what you're seeing is probably I mean may not be bulk, right? Because you said there's reconstruction of rubidium, and the rubidium has A and B phases. So the first question I have is that so what is really different between A and B phases? I mean, they both seem to be reconstructed, right?
They're both actually their lattice is the same, but the cube head pattern is different.
No, but I mean,
On the surface B, the cube head is more anisotropic. Yeah.
But is that because the differences in the rubidium, the number of rubidium on the system, the reconstruction of rubidium?
I don't think so. Actually, I don't know why. Maybe on surface B there's some local strain, maybe enhanced the nematicity.
I mean, if you imagine that the surface rubidium is, I mean, between these two phases are different from the bulk, then you would expect the superconductivity to be different, right? Because rubidium basically conforms to the structure, right? It's a rubidium iron arsenic, right? 122.
Yeah.
So
actually, we check the lattice is they are indeed the same. Their gap is slightly different.
I mean, the lattice, I mean, of course, the structure of the lattice will not change, but the electronic property will change, right? Because rubidium will contribute differently, right? So from that sense, I mean, so this result, I mean, seems to me, does not, conclude that the bulk has a C4 or C2 rotational symmetry, because it's rather strange, right? To have a tetragonal system with, nematicity.
Yes. Sure. STM is certainly only surface sensitive, right? And another problem is the QPI. We can also see this pocket, but the size of the pocket seems to be slightly different from the RPS method pocket.
So have you guys done RPS on this to see whether there's a splitting of the orbital?
Yes, we tried, but it's difficult to measure clean result. The surface is very sensitive.
Okay.
Yeah. The quality of the RPS data is very low.
Okay, thank you. And any other question for Tom? Oh, Taka? Yeah, please.
Yes, I have just a comment.
Yeah.
We recently measured the space heat and in-plane field rotation.
Right.
Region 1 to 2, and we found the two-fold symmetry.
Yeah, that's bulk. Yeah, it has to be
that's
bulk.
And which is consistent with his data.
Oh, okay. I mean, I'd like to hear your talk. Yeah, you're going to talk a little bit about that, right?
But not really, but
okay.
I can show the result. Yeah.
No, you're saying it's not going to be recorded since you don't want to be. Yeah. We're not recorded. Yeah.
Okay.
Any other question for Tom? Okay, if not,
actually, maybe can I just ask?
Yeah, sure.
A dumb, serious question. Is there? How good are these samples? It's a general. I'm not asking about your sample. Just in general, these potassium, iron 2, arsenic 2. These are presumably these are all single crystals, right?
Right.
And I just wonder. Let's see. What's the proper way of asking a question? Maybe let me ask you an empirical question. How many samples did you study for this?
I like 4 samples. Yeah. In total, we saw similar result.
Okay.
This single crystal we check with low diffraction.
So Hana, I'm sorry. Yeah.
Okay.
Are you done? Qimyang?
Thank you.
Can I?
Hey. Yeah. Go ahead.
Okay. Yeah. Just the small question. So, have you ever observed the nematic domains?
How large is the domain?
So
the nematic domain.
This is a good question. Actually, we didn't observe the domain wall of this nematic phase. which means the domain is very large.
Okay, I
At
see.
least at least hundreds of nanometers.
So you mentioned there is a crystallographic domain, so the pi phase shift. So in the atomic arrangement, I mean, you have the kind of domain boundary which is associated to the pi phase shift of the Lubezien arrangement, right?
You mean this
yes,
domain?
Yes, the domain 1, domain 2, and is the direction of the
domain is not. It's a domain of surface reconstruction. It's not
yes,
not a nematic domain.
So the question is, so the direction of the nematicity is the same between domain 1 and domain 2.
Yes, it's the same.
Okay, I see. Yeah. Okay, thanks.
So how do you understand that? How do you understand with these two domains, the nematicity, the orientation is the same?
But nematicity, I think it could mean that nematicity is from the bulk. It's not due to the surface reconstruction.
Yeah, this is very strange. Yeah. Okay. Okay. So if you're done, then we'll get Taka to speak.
Yeah. Thank you.
Yeah. Oh, Chimiao, can you delete the recording? Because Taka doesn't want his talk to be recorded.